On October 9th, 2022, at exactly 14:21 British Summer Time, something hit the Earth. Not a rock, not a solar flare. A wave of gamma radiation from an exploding star nearly 2 billion light-years away slammed into our planet's atmosphere with enough energy to measurably disturb the ionosphere, the electrically charged layer that sits just tens of kilometers above our heads. Instruments in Germany picked up the disturbance. Lightning detectors in India registered the surge. A simple radio antenna at Ireland's Dunsink Observatory, normally used to track the effects of solar flares, recorded a jump in signal strength that matched what you would expect from a medium-intensity eruption on the surface of our own sun. Except this was not from the sun. This was from a star that died before multicellular life even existed on Earth, in a galaxy so far away that its light had been traveling toward us for nearly 2 billion years. And when it finally arrived, it did not just pass through harmlessly, it reached down into our atmosphere to an altitude of just 60 kilometers and ionized the air. Astronomers named it GRB 221009A. Then they gave it a nickname. They called it the Boat, the brightest of all time. Statistical estimates published in the Astrophysical Journal Letters suggest that a gamma ray burst this powerful arrives at Earth roughly once every 10,000 years, and it was not even close. It was 1.9 billion light-years away. Now imagine what happens when one goes off in our own galaxy. Stay with me, because what I found while researching this video changed the way I think about the sky above us, the ground beneath us, and the strange, precarious accident that allows any of us to be here at all. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to where this story actually begins, not with the boat, but with the moment humanity first realized the universe was shooting at us without warning. In 1967, the United States Air Force had a network of satellites called Vela orbiting the Earth. Their job was simple and classified. Watch for the gamma-ray signature of nuclear weapons tests, specifically Soviet tests that violated the Partial Nuclear Test Ban Treaty. On July 2nd of that year, the Vela satellites picked up a burst of gamma radiation. It did not match any known nuclear test. It did not correlate with any military activity. It came from somewhere out there, from the cosmos itself. The Air Force had no idea what it was. The data was classified for years. It was not until 1973 that the detection was declassified and published by Ray Klebesadel, Ian Strong, and Roy Olson at Los Alamos National Laboratory. And even then, nobody knew what could produce that kind of energy. For the next 2 decades, the leading assumption was that gamma-ray bursts were relatively local phenomena, maybe something happening within our own galaxy, maybe magnetar flares or unusual stellar events. They were considered exotic, but not necessarily extraordinary in scale. That assumption held until 1997, when the Italian-Dutch satellite Bepo-Sax managed to pinpoint the precise location of a gamma-ray burst, and astronomers identified its host galaxy. It was not in the Milky Way, it was billions of light-years away. And that meant the energy involved was not large. It was almost incomprehensible. A single gamma-ray burst, lasting sometimes less than a minute, can release more energy than the sun will emit in its entire 10 billion year lifetime. Not twice as much, not 10 times as much, a quintillion times as much. That is a 1 followed by 18 zeros. These are the most powerful explosions in the known universe, and for decades we did not even know they existed. That was the first time the models broke, but it would not be the last. For a long time, the conventional understanding of mass extinctions on Earth centered on things we could see and measure: asteroid impacts, volcanic eruptions, dramatic shifts in climate. The late Ordovician extinction, roughly 440 million years ago, killed an estimated 57% of all marine genera. It was the second largest mass extinction in Earth's history, and for decades, scientists attributed it primarily to glaciation. The planet cooled rapidly at the end of the Ordovician period, and marine life, most of which lived in shallow tropical seas, was devastated. But there was a problem. Paleoclimate models, including work by Harriman and Patskowski, published in the early 2000s, showed that the late Ordovician glaciation could not have occurred without some external forcing mechanism. Something had to push the climate over the edge. The question was what? In 2004, a team led by Adrian Malott at the University of Kansas published a paper in the International Journal of Astrobiology proposing an answer that had nothing to do with volcanoes or asteroids. They suggested that a gamma-ray burst, a single 10-second pulse of radiation from a dying star somewhere in our arm of the galaxy, could have stripped away up to half of Earth's ozone layer. With the ozone shield gone, intense ultraviolet radiation from our own sun would have flooded the surface, and the extinction patterns fit. Organisms that lived in shallow water, exposed to sunlight, died at far higher rates than organisms that lived deeper. Species that spent part of their life cycle as surface-dwelling larvae were hit harder than species that did not. Survivors disproportionately came from deeper water and higher latitudes, exactly the populations you would expect to be partially shielded from a burst of UV radiation coming from a specific direction in the sky. Not proof. Mellott and his colleagues have always been careful about that. But a hypothesis that fits the fossil record, explains the mysterious glaciation trigger, and is consistent with the estimated frequency of nearby gamma-ray bursts, roughly 2 or more per billion years, according to rate estimates in the same paper. Now stop and sit with that for a second. A flash of light, lasting about 10 seconds, from a star that may have been thousands of light years away, might have reshaped the entire trajectory of complex life on this planet. Not through impact. Not through slow climate change, through a pulse of radiation that arrived without warning, did its damage in seconds, and left the atmosphere to unravel over the months and years that followed. But here's the part of this that stops being abstract and starts being personal. The boat, GRB 221009A, was 1.9 billion light years away, and it still reached down into our ionosphere. It still measurably altered the electrical conductivity of the atmosphere at an altitude of about 500 kilometers, according to data from the China Seismo-Electromagnetic Satellite published by Mirko Piersanti at the University of L'Aquila. Laura Hayes, a solar physicist at ESA, noted that the disturbance left an imprint comparable to that of a major solar flare, except it came from across the observable universe. Brendan O'Connor at George Washington University put it plainly. If it had happened much closer, it would have been really bad. We do not get to choose when the next one happens. We do not get to choose where the beam is pointed. The only variable that separates a spectacular light show from a mass extinction is distance. And distance in a galaxy containing hundreds of billions of stars is a matter of probability, not protection. But gamma-ray bursts are not the only thing the universe has been hiding from us. And the next secret is, in some ways, stranger and more unsettling, because this one is not out there in the distant cosmos. This one is woven into the fabric of reality itself. On July 4th, 2012, 2 teams of physicists at CERN's Large Hadron Collider, the ATLAS and CMS collaborations, announced the discovery of the Higgs boson. It was the final missing piece of the standard model of particle physics, the particle associated with the field that gives mass to every massive particle in the universe. The discovery was celebrated worldwide. What was discussed far less widely was what the Higgs boson's mass actually implied. The measured mass came in at approximately 125 giga-electron volts. That number matters enormously. If the Higgs had been heavier, closer to 129 giga-electron volts or above, the mathematics would have confirmed that the vacuum of space, the lowest energy state of the Higgs field, is absolutely stable, permanent, safe. But at 125 giga-electron volts, the calculations point in a different direction. The Higgs field's energy landscape, when you extend the quantum corrections to very high energy scales, particularly the contributions from the top quark, the heaviest known elementary particle, develops a second, deeper valley, a lower energy state that the field is not currently sitting in, but could in principle transition to. This is the false vacuum hypothesis, and it suggests that everything we see, every particle, every force, every law of physics as we experience it, may be a temporary arrangement. Not wrong, but not final. A quantum fluctuation, random, spontaneous, utterly unpredictable, could nucleate a tiny bubble of true vacuum somewhere in the universe. That bubble would expand outward at the speed of light, and inside the bubble, the rules change, the masses of particles shift, the forces between them reconfigure, the chemistry that makes atoms, molecules, stars, and living things possible simply ceases to exist. In 1982, physicists Michael Turner and Frank Wilczek laid out the implications in a paper published in Nature. A bubble of true vacuum could form somewhere in the universe and expand outward at light speed, and by the time we noticed, the very building blocks of matter would have already been rewritten. There would be no warning, no flash, no countdown. The bubble moves at the speed of light, so the information that it is coming arrives at exactly the same moment the bubble itself does. If you are the kind of person who finds this as strange and unsettling as I did while researching it, drop a like on this video right now because it genuinely helps this kind of content reach more people who would actually appreciate it. Now here is where it gets even more layered, because the universe is not just hiding sudden catastrophic threats. It is also hiding slow ones, things that are already out there moving through the dark, invisible, and undetectable until they are far too close to matter. In 2022, after more than a decade of painstaking observations using both ground-based telescopes and the Hubble Space Telescope, a team led by Kailash Sahu at the Space Telescope Science Institute in Baltimore announced the first confirmed detection of an isolated stellar mass black hole wandering through the Milky Way, not orbiting a companion star, not anchored to a binary system, just drifting through interstellar space in the Carina-Sagittarius arm, roughly 5,000 light-years from Earth, with a mass of about 7 times that of the Sun. The detection was only possible because of gravitational microlensing, a phenomenon where the gravity of a massive foreground object bends and magnifies the light of a star behind it. Without that chance alignment, the black hole would have been completely invisible. And here is the detail that changes the scale of the problem. Theoretical models estimate that there are approximately 100 million isolated black holes wandering through the Milky Way. 100 million objects, each capable of shredding any star or planet that drifts too close, moving through the galaxy with no companion, no emission, no signal of any kind. The one Sahu's team found is the only confirmed detection. The other 99,999,999 are still out there, unaccounted for. And then, in May 2025, astronomers including Yuhan Yao at UC Berkeley used the Hubble Space Telescope and the Chandra X-ray Observatory to capture the first image of a rogue supermassive black hole. Not a stellar remnant, but a massive black hole roughly comparable in scale to our own galaxy's central black hole A, wandering through a galaxy 600 million light-years away, 30,000 light-years from the center of its host galaxy. It had torn apart a star, producing a tidal disruption event that briefly outshone 10 billion suns. Yao estimated that such encounters happen once every 30,000 years for a given wandering black hole. But with potentially many such objects roaming many galaxies, these events may be far more common than we assumed. Think about what that means. Not only are there stellar mass black holes drifting invisibly through our own galaxy, but supermassive black holes, objects millions of times the mass of our Sun, can be ejected from galactic centers entirely and wander through the outskirts of their host galaxies, consuming anything that crosses their path. Now let's talk about what is happening right now in 2026. In June 2024, the SVOM satellite, a joint Chinese-French mission, launched into a 625-kilometer orbit with instruments specifically designed to detect and characterize gamma-ray bursts. Within its first 10 months of operation, the onboard gamma-ray monitor detected over 100 gamma-ray bursts. SVOM is now operating in coordination with NASA's Swift satellite, ESA's Einstein probe, and the Fermi Gamma Ray Space Telescope, the most comprehensive gamma-ray burst detection network ever assembled. Every day, these instruments collectively catalog bursts arriving from across the observable universe, building a statistical picture of how often, how powerfully, and from which directions these explosions occur. Meanwhile, the Vera C. Rubin Observatory in Chile is expected to begin its 10-year legacy survey of space and time, using its 8.4-meter mirror to survey the entire visible sky every few nights. One of its many scientific goals is to detect gravitational microlensing events, the same technique that revealed the first wandering black hole. Astronomers expect the survey to identify dozens of additional rogue black hole candidates. NASA's Nancy Grace Roman Space Telescope, expected to launch in 2027, will conduct similar time domain surveys of the galactic bulge. And ESA's Gaia telescope has already been mapping the positions of billions of stars, with lensing data expected to contain evidence for many more isolated compact objects. Łukasz Wierzykowski at Warsaw University, who co-authored the original rogue black hole discovery, has estimated that Gaia's forthcoming data alone could contain dozens of additional candidates. We are, for the first time, building the tools to see the invisible dangers that have surrounded us all along. And then there is the longest, slowest secret of all, the one that does not arrive in a flash or drift through the dark, the one that is built into the thermodynamics of the universe itself. The second law of thermodynamics, stated in its most memorable form by Rudolf Clausius in 1865, the entropy of the universe tends toward a maximum. Every process that converts energy from one form to another increases disorder. Stars fuse hydrogen into helium and radiate energy into space. That energy disperses. The hydrogen is finite. Within roughly 100 trillion years, the last stars will burn out. The universe will go permanently dark. After that, the only objects remaining will be white dwarfs cooling toward absolute zero, neutron stars, and black holes. If proton decay occurs, and grand unified theories predict it might, on timescales of around 10 to the power of 34 years, then even the dead stars and frozen planets will slowly dissolve into subatomic particles and low-energy radiation. Eventually, on timescales of 10 to the power of 100 years, the last supermassive black holes will evaporate through Hawking radiation, and then there will be nothing left. And not darkness. Darkness implies the possibility of light, just a void, expanding forever with a temperature asymptotically approaching absolute zero and no structure, no gradient, no mechanism for anything to ever happen again. Physicist Freeman Dyson once speculated that intelligent life might adapt by slowing its metabolism, living in brief computational flickers spread across unimaginable stretches of time. But eventually, there is no free energy left, not even enough for a single computation. Entropy wins, everything stops. Here's what I want you to take away from all of this. The universe is not hostile. That implies intent. It is indifferent. And in some ways, that is harder to sit with. A gamma ray burst does not aim. A wandering black hole does not hunt. Vacuum decay does not choose. These are simply the physics of a cosmos that operates on scales and principles that were never designed with us in mind. And yet here we are, on a small rocky planet, orbiting an unremarkable star, in a galaxy containing 100 million invisible black holes, and bathed in radiation from explosions that occurred before this solar system existed, and we are still here. Not because the universe is safe, but because, so far, the geometry has been favorable. The beams have missed, the black holes have drifted past, the vacuum has held. Every generation of life on this planet has existed inside that margin. Every species that has ever evolved, every civilization that has ever risen, every single moment of human consciousness has unfolded inside a window of stability that the universe is not obligated to maintain. We cannot control when the next gamma ray burst is pointed our way. We cannot see the black holes drifting between the stars. We cannot test whether the vacuum we live in is truly the ground state of reality or just a ledge on a much deeper hill. But we can look, we can measure, we can build the instruments and ask the questions and refuse to stop paying attention. And there is something in that, something defiant and necessary and deeply human that matters, even if the universe never notices. One species, one planet, one thin atmosphere, balanced on the edge of everything we do not yet understand. If this is the kind of content that makes you stop and think, subscribe and hit the notification bell so you do not miss what is coming next, because I am already researching the follow-up and the story only gets stranger from here. Drop a comment telling me which of these threats surprised you most. Was it the gamma ray burst that already touched our atmosphere? The 100 million invisible black holes? The possibility that reality itself is temporary? Let me know. And if you know someone who would want to hear this, share this video with them, because these are the kinds of stories that deserve more than the silence they are getting.